Hi guys, welcome to section B of chapter 5. A lot to talk about in this section. So let's get started. I told you we're going to talk more about those covalent and ionic bonds. Let's jump into the covalent bonds. Remember, those are the ones that just share the electrons. They're not actually transferring them. Nothing's becoming an ion. And so it's almost like the electron is flying around both atoms because it's splitting its time between them. Some common covalent bonds are between what's known as a diatomic molecule, and that just means it's made out of two atoms, di meaning two, okay? So let's look at a couple of examples here. Chlorine has 7 electrons, okay? We know there's 7 valence electrons. It only needs one more. And so instead of always ionically bonding with something with one atom and actually taking it from it, sometimes it'll just share with something that also needs one electron, okay? So two atoms of chlorine can actually bond together, and they're each sharing that extra electron. Okay, so you can see let me get my pen. There we go. Let's look at the blue electrons here. Okay, there's 7 blue electrons, and it's sharing that eighth one from the red side. So that red one is going to share its time with these, okay? Well, the red ones also need one, so this blue one is going to share its time over here. And because of that, these two atoms will stick together, will be bonded together because of that shared atom, okay? Oxygen has 6 valence electrons. It only needs 2, and so 2 atoms of oxygen coming together, they will each share 2. And so again, here's a total of 8. Here's a total of 8, and they're sharing those 2 in the middle there. And we actually show that bond with this double line here. The bond between chlorine is a single line because it's just sharing a pair. Oxygen is sharing 2 pairs, so we show 2 lines. And then nitrogen has a triple covalent bond. Nitrogen has 5 valence electrons, so it needs 3 more. And so they're going to share 3 on each side. Since there's 3 pairs of electrons being shared in the middle there, that is indicated with 3 lines in between. Okay, and we can see that more over here. So this is the Lewis dot structure for some basic compounds here. So we have 2 hydrogen molecules. Remember, each hydrogen has 1, but they want 2. So they'll come together and they'll share that pair of electrons. And so it's drawn with this dash in between to show. Anytime you see a single line in between two elements indicating a chemical bond, it means that it's just involving the 2 electrons, okay? Chlorine we already did, oxygen we already did. There's that double bond, okay? So they're sharing 2 pair of electrons. Nitrogen, they're sharing 3 pair of electrons. Fluorine, is the same as chlorine, okay? They each just need 1 more. So they're going to share that pair in the middle. But now let's look at a 3-element compound, okay? Let's look at carbon dioxide. Carbon right there in the middle only has 4 valence electrons. It needs 4 more valence electrons. But I also have 2 oxygen molecules that come with 6, so they each only need 2 more. So what's going to happen is this oxygen is going to share 2 of its electrons with carbon. Carbon's going to share 2 of its electrons with the oxygen. When you count those all up, that gives oxygen 8 electrons. Same over here, it's going to share these, okay? Now, carbon's not transferring those. It's actually sharing all of these. So there's carbon's 8 shared electrons there. And all that sharing, all that moving around is really holding them tightly. But you can see that they're sharing a double bond. They're sharing that pair there. So that's why we've got those double dash lines. Those are all indicating covalent bonds, okay? Let's keep talking about covalent bonds. That last example, the CO2, is known as a polyatomic molecule, and those are just molecules made of more than 2 atoms. Water is also a polyatomic molecule, okay? But the sharing of those electrons isn't always equal. Sometimes some of the atoms are a little, they don't play that nicely. They want to hang on to the electrons more. They don't share equally, okay? And that's when we start to get this thing known as polarity. It's not ionic. There's not a complete transfer of electrons, and there's not a complete charge. But the electrons spend more time with one atom than the other. So it's an uneven distribution of the electrons, and it really depends on the electronegativity of the atoms, okay? So water, oxygen is like the second or third most electronegative atom there is. And so it really hangs on to the electrons more. Hydrogen's fairly weak, and so it gets to share these two here, but really they're sticking closer to oxygen, okay? They just like to hang out by oxygen more. And so we get, don't worry about that symbol, but we get a slight negative charge to the oxygen because those electrons are spending a little more time there, and we're left with a slightly positive charge on the hydrogens. Again, this is not an ionic charge, but it is enough to make water polar, and it gives water some really unique properties. This is why water is called sticky. Things like surface tension and capillary action are because of those water molecules sticking together, okay? I don't know if you guys remember the experiment I did with the water droplets on the penny. It makes that really obvious dome. It's because water's sticking together. This is why bugs can like just walk on water. This is why a belly flop hurts. Water doesn't like to split apart. It hangs on to itself because of those slight charges. All right, let's talk about sulfuric acid. Sulfuric acid is this right here, H2SO4. Okay, so that means there's 2 hydrogen, 1 sulfur, and 4 oxygen. Okay, if you look on the periodic table, you'll see that sulfur has the same number of valence electrons as oxygen does. So we're going to put sulfur in the middle here with its 6 valence electrons. And I'm going to draw them like this: 1, 2, 3, 4, 5, 6. Okay, so it needs just a couple more. All right, so I'm going to put an oxygen, and it's going to get a little complicated. I'm going to put an oxygen here. I'm going to put another oxygen here. Got that a little close, actually. Let me erase that. Draw it a little farther out. Dot, dot, dot. Okay, another oxygen up here. Dot, dot. 1, 2, 1, 2. Okay, so I'm not done yet. I'm almost there. Okay, so these are sharing 2 pairs, so those are actually going to be a double bond. Okay, and you can see that now oxygen on the top and oxygen on the bottom has a total of 8 electrons because it's sharing those with the sulfur. Okay, let's look at the oxygens on the side. Okay, they're sharing a single pair, so a single bond here. Okay, so I've got 2, 4, 6. I need 2 more electrons on each of those outside oxygens. So I'm going to put my hydrogens there. So remember, hydrogen only wants 2. So there's the 2 for hydrogen because it's going to share 1 with the oxygen. Then those 2 added with, so I've got 2, 4, 6, 8 on those oxygen right there. Okay. I don't think I have a backup button. Yeah, no, it just takes me to the other slide. So we would draw this a little neater. Like this. Okay, remember those dashes imply that they just share 2, and the double bonds, they're sharing 2 pair of electrons, okay? And then they would all have 8 valence electrons, or 2 for the hydrogen, but they're full because of the way they share. They all have a full energy level. And this is what determines why certain compounds exist, okay? Because it's not just a random assortment of elements, it's elements that can come up with this special octet rule. And it might be some pretty complicated bonds, complicated formulas. We tend to write them down like this, but this is actually how they would bond together, okay? Chemistry 101. All right, now let's talk about ionic bonds. Remember, the ionic bonds actually transfer the electrons, okay? And this occurs with atoms that have very different electronegativities, okay? They're not going to share at all. One electron either leaves or is gained, okay? When one is, when an electron gives an electron away, it's known as a donor. When it gives it away, it loses a negative charge, so now it has more protons, so it has a positive charge. But then the other one will take that electron, that's known as the receptor, and now it has an extra negative, and so it has a negative charge. And we talked about that last section when we talked about the sodium chloride. Sodium is giving away its extra electron, and so it's becoming negative. It's becoming positive because it gave it away. Chlorine, really that's a positive, not a star. Chlorine gains that electron, and so it's more negative, and so now it's negative, okay? Chlorine would be the receptor. And it's that different charge, it's that attraction of the opposite charges that holds those elements together, okay? All right, so this is probably gonna look like a foreign language here. I would suggest pausing the video at this point and kind of just paying attention to these dots, okay? We've got water up at the top here. This is a covalent bond, okay? Remember, each dash implies a pair of electrons. So I've got 2, 4, 6, 8 for the oxygen, and I've got 2 for each of my hydrogen. That's why that works, okay? The nitrogen and the 3 hydrogen there, that's ammonia. Nitrogen has 5 valence electrons. It needs 3 more. Each hydrogen has 1 valence electron. It needs 1 more. And so they are going to share those, okay? And so this 2, 4, 6, 8 gives nitrogen what it needs. And then each of these gives hydrogen the 2. Okay, then the CH4 down at the bottom, that's methane, same thing. Carbon has 4 valence electrons, it needs 4 more. Each hydrogen has 1 and it needs 4 more. So they are each sharing there. Each of those dashes means 2 electrons, okay? The ionic bonds over on the other side, we already did the sodium chloride, but let's look at magnesium and oxygen, okay? Oxygen needs 2, magnesium has 2 it wants to get rid of. So magnesium is going to lose 2 electrons, making it a positive charge, a 2+ charge. Oxygen is going to gain 2 electrons, giving it a 2 negative charge. And we always put the positive and the negative after the number for the ions. I don't know why, they just do. And then we've got this down, we've got 1 calcium, it's got 2, and we've got 2 chlorines. Each chlorine needs 1 additional electron. And so it's going to get, each of the chlorines is going to take 1 from the calcium. So the calcium is going to give up both of those extras, giving it a +2 charge. Each of these chlorines is going to take 1, giving them a negative charge. You don't need to put the 1, it's just the negative sign, okay? Similarly down here with the 2 potassiums and 1 sulfur. Sulfur has 6, it needs 2 more. So it's going to take 2 from the potassiums, giving it a charge of a 2 negative. The potassium each lost 1, giving it a positive charge. And just that single positive means +1, okay? I know, who knew there would be so much math in this, right? Don't you love integers? Yay. All right, guys, see you later.